Okay, so welcome to task 3 of the ISP for Unit 4, Further Mechanics and Electromagnetic Fields. So this week's is going to be looking at a bit more detail on electromagnetic fields now. I'm going on to Coulombs law and how to calculate the forces between two charged particles and the experiments that we can use to demonstrate them. So mainly looking at Coulombs law, so forces between charged particles here. So the explaining everything task. Well, I've added a picture to my version of it because I think it helps me explain what's going on. To check that's the only one, yep, so it's just one explaining everything task for this. So the idea is we need to describe how charged particles interact with each other, include a description of the experiment that can be used to show how charged particles interact. So here's the main experiment that can be used to show how charged particles interact. So if these two are charged, okay, there's a distance between them of r. They interact with each other. So this is capital R, we use a small r. So therefore there's forces acting on this charged particle over here. Okay, so there's going to be a gravitational force or weight pulling it down. There's the electrostatic repulsion because these are the same charges pushing it across, and there's tension in the string pulling up as so. So from that, if you know the angle from the vertical, you could draw a vector diagram which allows you to sort of calculate what's going on here. So remember, the size of this electrostatic force here must be equal to the horizontal component of tension, because of the fact that's the only other thing applying any horizontal force. And the size of weight must be equal to the vertical component of tension, because again that is the only other thing applying any vertical force. So the only other horizontal force to balance out the electrostatic repulsion essentially comes from tension, and the same with weight. The only other vertical force to balance out the weight comes from tension. So if you resolve for your x and y of tension, as we are doing in this little bit over here, you could figure out the size of the forces acting on it. Excellent. The only other thing to really mention is the fact that we've got an inverse square law for Coulombs law against essentially for the interaction of two charged particles. So it's k q1 q2 over r squared. F equals k1 q2 over r squared, where F is the size of the force, k is a constant. So I think it's 1 over 4 pi epsilon naught, where epsilon naught is the permeativity of free space. Q1 and Q2 are charges, and R2 essentially is the distance between two objects. So the distance between the two objects squared. Okay, so it's an inverse square law. F is directly proportional to 1 over r squared. Right. So let's get stuck into the questions. So hopefully you've included all of that and you're explaining everything. Straight to the questions. So I think it starts in question 6. Just double check. Yeah, there we go. State in words the formula which gives the electric force between two charged particles. Okay, so that's essentially this equation here, but we want that in words. So the idea is the force between two charged particles is directly proportional to the product of their charges and inversely proportional to their the distance between them squared. Okay, so the idea is that F is proportional to 1 over the distance between them squared. So F is inversely proportional to the separation squared, but F is also directly proportional to the product of the charges. So remember, product is where you're multiplying them, sum is where you're adding them together. So the product of the charges. Okay, so that's 6a. 6b, what is the base units of the constant in this formula? So you need to rearrange for k, and go from there. So essentially you want each of these in base units and going from there. Or you could rearrange for k and then figure out a base unit. So let's rearrange for k first. So k is going to be equal to fr squared over q1 q2. Okay, so that's just a rearrangement of that equation there. Okay, so you've got your f, you bring your r squared up, you bring your k's underneath. Well, that is therefore newtons meters squared over coulombs squared, because that's coulombs times by coulombs. So, newtons we know is kilogram meters per second squared in base units from F equals m8. You should remember that from AS physics. Okay, that's going to be now multiplied by meters squared. And in terms of base units of the underneath, remember that's amp squared second squared, because Q equals IT, so it's going to be amps times by seconds, but because it's squared, it's amp squared, second squared. So that's everything now in base units. It is now literally as straightforward as cancelling. Okay, so our top, if we multiply those through together, you end up with meters cubed, so kilogram. Let's get this back into shot. Meters cubed, but we've got seconds to the -1 divided by seconds to the 2, so that becomes -2 because you're dividing by it. So it's essentially seconds to the -3, and we've also got amps to the -2 because that's also being divided as well. So that's what we end up with. Just checking to see that I haven't missed anything out. Got a feeling I missed out one of the seconds. Oh yeah, right. There's a mistake over here that's squared, because meters per second squared, so that would end up being 4 then. I had a feeling I made a small mistake there. There we go. Okay, so that's our equation in, the units of K in base units. Okay, so nice 3-mark question to get. Okay, so we've got a practical where we've got a charged ball suspended off a charged sphere, and they're asking us to draw a free body force diagram for this ball. Okay, so this is sort of stuff we've done before. You've got a picture of one of those above. Okay, it's straightforward. So you end up with something that looks, just get the top of a piece of paper to shot. There we go. Okay, you end up with something that looks a bit like this. You've got a tension acting up there, you've got weight acting down here, and you've got repulsion acting over there. So tension, weight, and that's F for the Coulombs law force there, and your angle of theta is essentially that one there. Okay, nice. So the weight of the ball is given by that, is W. Show that the force of repulsion on the suspended ball is given by W tan theta. Okay, so we can do this into a closed vector triangle, like so. Okay, there's our theta. Weight is going to be the one acting down, that's over here. So we haven't got the hypotenuse, they want the, we have the adjacent, they want the opposite, and we have the angle. Okay, so it's TOA that we're using. They want the opposite, so it's going to be the adjacent times by tan theta. So in other words, we've got W tan theta. Straightforward as that. Nice, easy question. Oops, skip too far ahead. Nice, easy question for 2 marks. Okay, they're asking us to calculate the values of the Coulomb law forces for these two over here. So essentially what you've got to do is you've got to do the calculation here to figure out the value of K, Q1 and Q2, because remember they're not changing the Qs. So if you figure out the value of K, Q1 and Q2, that's a constant in itself. So then therefore you just work backwards through that to figure out your 2 forces for this one's over here. So once you've figured out what your K is, you can go from there. Okay, so once you've figured out what your K is, you can work at what your K, Q1 times Q2 is, you can work backwards to figure out the size of these 2 forces here. And I'm wanting you to write the answers into the table correctly as well. So it's 4 marks, very, very straightforward. So it suggests in practice what is necessary for the student to take measurements quickly using this arrangement. Remember, charge leaks away. So there's an idea of discharge of charge that happens quite quickly. So it's charge leaking away, so you need to do that very, very quickly. So genuinely a nice 10-mark question. You can see that it comes up quite often, considering it's asked again. Right. So we've got, again, similar sort of experiment. We've got 2 charged balls and they're moving away from each other due to electricity propulsion. She put the dimensions on there in terms of distance and in terms of length. She thinks that she can make accurate measurements if the balloons are at an angle of 1.5 degrees or more from the vertical. Add to the diagram to show all the forces acting on the balloon on one of the balloons, hence showing the minimum charge Q that she needs on each balloon must be about 0.1 coulombs. Assume that each balloon behaves as though the charge will contract at the centre. Okay. So we have the angle that's required. We need to essentially draw the forces on there. So it's the same as above. Okay, same as above. So if we're treating the one on the right, so that's 1.8 meters. Okay, exact same forces, exact same diagram. The mass of each balloon we know is 0.0018. Okay, therefore we can figure out the size of this repulsive force. Okay, so the mass is 0.0018, so the weight is going to be that times by 9.81. You can figure out the size of this repulsive force on the opposite, just like we did before. Okay, so once you've done that, just by doing that equation there, so exactly the same as the first part of the question. So once you figure out the force, you know the R that's required, therefore you can figure out your Q squared, so in other words your Q1 times Q2, they're saying they're equally charged, and then you square root that to figure out, so essentially using this equation with it. The radius you've been given as 0.5 meters, added to whatever you figure out by Pythagoras is the distance over here, so you know the length of this, and you can say, not by Pythagoras, by trigonometry, you know the length of this one here, or this one here, and you know the angle, and therefore you can figure out the distance that this is, adding that to the 0.5 twice for each of those. So you figure out this extra distance on both of them, and you add them to that 0.5, and therefore allows you to figure out your R. You square it to figure out your R squared. You know your F from the calculation above, you know K, it's a constant, so you're going to figure out your Q1 times Q2, so in other words your Q squared, you square root that, it should be close to 0.1. Okay, so again, a nice question to get, 6-mark question, a lot of people will struggle with that one. Okay, so that sums up our video, that sums up the whole of task 3 for ISP, electromagnetic fields and further mechanics. Just to show you that final calculation, just to make sure you completely got the idea. Okay, so the first part of it is labeling the forces. Okay, the second part of it is using that equation and getting to it from this. Okay, so they're using t cos theta and t sin theta, but you know that t cos over t sin is equal to tan, so you can do it straight away with tan, like we mentioned above. Okay. Here's the idea of that 1.8 sine 1.5, which essentially gives you that extra distance, but then multiply by 2 because it's done twice. So that's the overall distance, that's your R essentially. So that's how you get that mark there. And there's the idea of that Q being Q squared, and therefore figuring it out as the Q squared rather than Q, then square rooting it to figure out your Q. Okay, so thank you for watching, guys. Thank you very much for working through these two questions together. Very tricky questions, and you'll get your head completely around Coulombs law by watching these. Sorry about the beeping, that's just my lunch ready, so I'll end the video there. Thank you very much for watching.